In this video, we're going to start talking about evaluating limits. So if we have a limit and we have the formula of the function, for example, the limit of x squared as x approaches 2, our first recourse will just be to see, can we simply plug in? And here, of course, we can plug in perfectly fine, plug in 2, and we get that the limit is 4. Again, y equals x squared, that's a nice smooth polynomial. So the limits are actually not all that interesting to talk about because, again, that is a function where it looks like it's going, it always winds up going. Becomes much more interesting if we start looking at a limit like this. We have a function like the limit as x approaches 2 of the function x squared minus 5x plus 6 over x minus 2. Now when we plug in, we get 0 over 0. And 0 over 0, of course that does not equal 0, that does not equal infinity. That equals something that mathematicians call indeterminate. In other words, it's hard to tell exactly what it equals. It could be almost anything. That's what it means to be indeterminate. And it means in particular that we have to do some more math to figure out the exact value of it. So here you may notice that what we can do with that polynomial on the top, that quadratic on the top, is we can factor it. And in fact, it factors very nicely to x minus 2 times x minus 3. And then we have a factor of x minus 2 in the denominator, and we can cancel. And so this is going to be the same as the limit as x approaches 2 of x minus 3. Well, now we can plug in, and we get 2 minus 3, which is negative 1. It's very important to make a distinction here. We're actually talking about two different functions. Function number 1 is x squared minus 5x plus 6 over x minus 2. And then g of x equals x minus 3. Now the curious thing is, everywhere where f of x is defined, it equals g of x. However, these two are not the same function because g of x has a domain of all real numbers, and f of x has at least one number missing from its domain. X can't be 2. So g is something that we are going to call a continuous companion function. F of x is a bit of a problematic function insofar as it has a hole in it. G of x is a very good friend to it. A continuous companion function has exactly the same values of f of x everywhere except where f is undefined. And of course g is defined. And it turns out that if you can figure out the continuous companion function, you can just plug in the value of x into that, and that will equal the limit. So once again, another example of factoring. The limit as x approaches 2 of x cubed minus 8 over x minus 2. Well, again, we plug in, we get 0 over 0, so we know we have to do a little reconfiguring in order to get a meaningful answer here. Here, what we have to do is factor the cubic. Now, you may remember that that factors into x minus 2 and then x squared plus 2x plus 4 over x minus 2. Again, cancels. We plug into the continuous companion function, and what we get is 4 plus 4 plus 4 equals 12, and that is the limit. So factoring is often one very useful trick to get something to cancel so that we can evaluate a 0 over 0 limit.